you can do in your notes as well. We're going to start off talking about Boyle's Law, which is the one we did right before break, and you handed that in. And so, page 370 is where we're going to be at. And on Boyle's Law, it says that pressure and volume are inversely related to one another, keeping temperature in Kelvin and the number of molecules constant. Alright, so if that's the case, we solve for K, which is the constant, by doing what with pressure and volume? Did we multiply them or did we divide them to find a constant? Okay, if it's inverse, we're going to multiply to find a constant. That's what you did on the lab. You multiplied, you found that method gave you a consistent, similar number each time. So if we take P times V, then we'll get a constant. So let's say that we have a situation where we have a sealed container under a certain temperature, like a balloon or a syringe, and we vary the volume, the pressure will change with it, inversely. It'll go, you increase the volume, the pressure goes down. You decrease the volume, the pressure goes up. Right? So we have that relationship. So if we don't let any gas in or out, and we don't change the temperature, then we can use this law to solve problems. And this is a setup that we're going to use. It's going to be P1 times V1 equals P2 times V2. So I'll tell you what the numbers mean. They're just two different conditions. Like we did the syringe, volume 1 would have been 10 milliliters, and then the new volume, we'd push it into 5 milliliters. So you guys know what will happen to the pressure, right? If you go from 10 to 5, what happens to the pressure?
It's doubled.
It's doubled. Okay? Volume's cut in half, pressure doubles. So what we'll do is we'll use this setup to solve for a problem where temperature remains constant and we don't let any air in or out of the system that we're studying. And the system would be whatever we're looking at studying. So on the bottom of page 370, okay, there's that practice problem. Basically what it says, you have a balloon, all right, helium balloon. Measure the pressure. It's 1 atmosphere at the beginning. The volume of the balloon was measured to be 500 milliliters. We let it go. It goes up in the air. It goes up to a certain altitude, 6.5 kilometers above. All right? Now, there's a pressure sensor maybe attached to it, and it measures the pressure of that at that place and the temperature says it's the same. So the pressure sensor reads 0.5 atmospheres. All right? So what we're going to do when we set this up, I'm not going to put any numbers in until I solve for one of these variables. I'm going to have to solve for one of the variables. So what I'm going to do is I'm going to put P1, V1, P2, V2 to identify all my different pressures and volumes. Lots of times, 1 means initial at the beginning. So the balloon was at surface, and the pressure was 1 atmosphere. And then the volume was measured at 500 milliliters. As I got to that new altitude, the pressure was measured to be 0.5 atmospheres. So then it's asking, what's the volume of the balloon at that point in time? So did the balloon get bigger, do you think, or does it get smaller? Bigger. 1 to 0.5, less pressure on it. Less pressure means the volume can get bigger, okay, at the same temperature. All right, so we know that, but we want to do the calculation just to make sure. So we're solving for V2. You guys know how to set that up to solve for V2, right? What would V2 equal? V2 equals, so we divide what out on that side, we have to divide pressure out, right? So we're going to divide pressure out on both sides. the P2 pressure. So V2 is going to equal P1 times V1 over P2. Any questions with that? That's all you're doing. My suggestion, I know Dr. Christian does the same thing. She and I agree. Why put numbers in until you get everything set up? It's so much easier just to solve the symbols. You don't have to write units. All you have to do is write the symbol, and that's it. So that's what I'd like you to do. So then you can just substitute in your different values. P1 is 1 atmosphere. V1, 500 milliliters. And P2 is 0.5 atmosphere. Any questions with that? And then your answer, once you do that, what do you guys think? Before I plug this in, you guys know what the answer is going to be, right? 1,000. Because it doubles, right? Pressure is half, volume doubles. So sometimes you don't even have to plug them in because the numbers are so easy to look at. This one's just a good practice one. That would be your answer. You also should notice that the units, we want to start paying attention to units and how they cancel. And that's another way we can see and make sure our units are lining up correctly. Any questions? Thoughts on that? Alright, so to do this problem, temperature has to remain constant. It'll say right in the problem, temperature remains the same. Alright, doesn't change. Alright, so the next one we did, you guys did this, did Gay-Lussac's law before break on Tuesday. We got all the information, and yesterday we just printed off graphs because we didn't have time on Tuesday. Went through some questions you might have. Find absolute zero, we found that. Wrote that down for question 7 using our graph. Get with your partner. If you were gone, get with your partner. Kind of see what they did. I don't mind them sharing that information with you, especially the absolute zero and how they found it. You just might ask them how to do that, but you can give that to them if you want. This one looks at temperature. So we have this flask. We go along, we put it in colder to warmer to hot. And the temperature change and the pressure change, right? So we realize that that's a direct relationship. That temperature goes up, pressure goes up. Molecules start moving faster. Okay, so then how did we solve for the constant on that one? Remember? How did we solve for K? Yep.
Pressure divided by temperature.
P divided by T. Now, something we have to be conscious of is that that temperature has to be a specific temperature. What's it have to be? To plug in, to do a calculation of constant, it has to be Kelvin. That's why we had that third column, so that you can figure out Kelvin. So this has to be Kelvin. Right? You won't be able to use Celsius to get the right answer because Celsius will have negative numbers and it has a different starting point on the scale. So we have to have Kelvin. We have to use Kelvin. Right? So don't get confused with this K because that K means constant. And then temperature has to be Kelvin. So we're always going to add what to Celsius? 273. 273 each time. And what happens on this one, there's two things that will happen that will get students to where they can calculate the right answer. One is they're putting Celsius in the problem instead of Kelvin. So that right away, that gets you a wrong answer. So I'll try to show you a method that keeps you from making that mistake. All right? Another one is students have a hard time solving because they got to do 2 steps to isolate a variable that's in the denominator. So they're not sure what those 2 steps are. You should by this time in algebra, but I'm going to try to simplify it so that we're going to eliminate one of those steps and make it easier. Okay? So, just like the last one, P1 times V1 equals P2 times V2. This one instead is going to be P1 over T1 equals P2 over T2. Right? So what I'm going to do, when I give you a test or quiz, I'm going to give it to you in this form. I'm not going to change the form I'm going to give it to you in. But what you can do, knowing how to make this easier to set up, what I would do is I would cross multiply these symbols. Okay? Cross multiply those symbols, and then that will get me a better setup to start with. Okay? So I'm going to have P1. I'm going to have to do something here real quick. Ghost started moving this. Doggone Ghost.
There you can.
Okay, so I'm going to take P1 times T2 equals P2 times T1. Does anybody have questions why I'm doing that? Does that make sense? Okay. So what it does is it allows me to not have to do two steps. When I solve for a temperature, all I'll have to do is I'll have to multiply both sides by that T2 temperature, and then the next step I'll have to get it by itself is divide by the other side. And so it just makes it easier. Just cross multiply the symbols. Boom. Problem is, students will do this and they'll go P1 times T1 equals P2 times T2. And if that's the case, that's an inverse relationship, and this is not an inverse relationship, it's a rect. So you have to set it up based upon P1 over T1 to get your constant. But you can manipulate it and change it. I like doing that. It simplifies it. So then when I go through the problem on page 374, I can do it the same way as what I did earlier. So it says that we have initial pressure or initial temperature of 120 degrees Celsius. You know what I'm going to do? I'm going to put my P1, T1, P2, T2 over here. And then where it says 120 degrees Celsius, you know what? I'm not going to plug it in here. What I'm going to do is I'm going to change it before I put the number in here. So 120 is what in Kelvin? 120 plus 273 is what? 393 Kelvin. You know what? I don't make a mistake because I'm rushing or because I'm not paying attention. Or some of you I know don't write units behind your numbers. So you would have wrote 120 and then maybe not know any different and then plug it in. So if you just right away realize T1 cannot be Celsius and just do it before you substitute it in, that would be the best thing to do. That's what I would do when solving for it. The pressure is 1.07 atmospheres. It says that the new temperature is 205 degrees Celsius. So what would that be in Kelvin? 478. You know what? And then that way I don't make a mistake plugging in my numbers. And then P2 is what I want to solve for. Go ahead and solve for that, if you would. Solve for P2. See if you come up. Use your logic of understanding if the temperature goes up, pressure has to go up. Temperature goes up, pressure goes up. So use, if you get an answer that's lower, that's not good. If you have all those over here, you'll have to switch it around. You got to solve for P2. Now, I switch them around, the symbols around, and then plug my numbers in at the very last point. Then I don't have to worry about switching numbers around. I just switch symbols around. So it'll be P1 times T2 over T1 gives me my new pressure. And I just plug in my numbers. Kelvin cancels. What'd you get for an answer? Did you get 1.3? Okay, that would be the answer. 1.3. Make sure you're writing the units correctly. Pressure should be in atmosphere, so 1.3. Atmosphere. Temperature goes up, pressure goes up. Good, you got it. Okay. This last one will go a little bit quicker because it's the same thing as Gay-Lussac's law, but we're looking at volume. So the setup's going to be the same. Instead of P, we're going to have V. Same setup. Okay, now this law we did not investigate, but all we had to do is an inverse and direct, kind of see how that works. Okay. So on this one, real quick, I'll write out same information. V over T, get your constant. So that means that if we don't change the pressure and pressure remains constant, then we can go V1 over T1 equals V2 over T2. Go ahead and cross multiply. Well, that's what I would like to do. I go V1 times T2. Again, realize students like to go V1 times T1 for some reason. I think they like Boyle's law. Just always remember, when you got temperature, it's always going to be the opposite temperature that you need to multiply. So if you keep that in mind, then you won't make that mistake. So V2 times T1. Okay. So the problem we'll do is number one, page 372, which is the prior page. And then all we're doing is we're looking at the sample of gas. It has a volume of 752, so we'll over here we'll go V1, T1, V2, T2. Usually they'll put the volume and temperature together, and the volume and temperature final together, and then they'll tell you which one you have to solve for. So sample neon gas has a volume of 752 milliliters. The temperature is 25 at 273 is 298 Kelvin. V2, we don't know. What's the new volume? And the temperature goes up to 100 degrees Celsius, so add 100 to 273 would be 373 Kelvin. And you got your numbers, and you just have to solve for V2. So on that one, solve for V2. Temperature goes up, volume has to be bigger. Yes?
How did you get 100 plus 273?
273 is what you use when you convert Celsius to Kelvin.
But in the book it's 50 degrees.
Well, we might be looking at a different problem. I'm looking at practice problem number 1, bottom page 372.
Oh,
So,
yeah.
yep. Good question. See where we're at. Yep. So then, when you solve for that, you plug your numbers in. After plugging your numbers in, I'll let you do that. The answer for that one is 941. Okay, we didn't do one. I should have did one where you had to solve for temperature. But temperature, if you solve for it, what's your units going to be? Kelvin. Sometimes students have, yes, I don't know. Okay, so V1, 752 times T2, 373.
Oh, I put it on.
Yeah, and that's what happens, Carly, because once you get going, you want to go in line, and you just have to make sure that you're using the right temperatures. That's a common mistake. If when you do this, if it asks for what's the temperature in Celsius, they'll ask you. Guess what? You still have to have it in Kelvin. Then you have to convert it back. So if I get an answer out, that would be temperature in Kelvin would be like 300 Kelvin. Then I have to convert that back to Celsius by subtracting 273. Okay. So don't think you have to plug in Celsius if they ask you what's the temperature in degrees Celsius. You have to convert it to Kelvin, plug it in, and then subtract 273 to get Celsius later on. All right. The problems that would like you to do would be these 6, and you can put them in your notes.
In our notes, that's what we want to
Won't turn them in. They have to be done to get credit for the completion grade, but you have 6 there you can work on. Same as what I've done. I just got to make sure what are you given? Volume and pressure, that's Boyle's. Pressure and temperature, that's Gay-Lussac's. Volume and temperature, that's Charles. Okay?